we're going to find the total or the equivalent capacitance of this combination of capacitors. It's a really complicated combination, but the reason why we'll do this and walk through it and why I want you to see it is because it's a really great exercise in problem solving. I've labeled each of these capacitors with a letter, so I can refer to them below here. Our first capacitor has a capacitance of 4 microfarads. I'll call that capacitor A. Capacitor B has a capacitance of 1 microfarad. Capacitor C, a capacitance of 3 microfarads. D, 6 microfarads. E, 2 microfarads. And F, 8 microfarads. And again, we got to find the total capacitance of this combination of capacitors. So how do we do that? Here is the problem-solving process that we're going to use in order to solve this problem. And it's similar to how we will solve problems that look kind of like this, except with resistors instead of capacitors. Our strategy here will be to look at our combination of capacitors and try to reduce it down in multiple steps and reduce it down from this combination of capacitors all the way down to the equivalent capacitance of one single capacitor that you could replace with all of these capacitors in combination. And we have to work in chunks. The first thing that we're going to do is identify some capacitors that we can combine together in order to take us to the next step. So for example, what I've drawn right here, I've got my capacitors. This capacitor is in series with these two in parallel. These two capacitors are in parallel with this one in series, and they both are in, these branches are both in parallel with each other. But let's break it down into some bite-sized chunks. What we can do is combine these two capacitors together in parallel to get an equivalent capacitance that we could replace these two with. Okay? And then that's going to be the capacitance of this capacitor right here. Okay, so if we look here at our next diagram that we could draw after this one, we still have our 4 microfarad capacitor here. We're going to combine these two in parallel to give us a new equivalent capacitance for this capacitor that we could represent right here. We're going to combine these two capacitors in parallel. That will be represented by this capacitor right here in this new diagram. Ooh, that's squeaky. We'll find that capacitance, but then the capacitance of this capacitor is still this 8 microfarads. So this is still 8 microfarads. So to go from this step to this step, as we reduce our total capacitance in smaller chunks, is to combine these two capacitors in parallel and these two capacitors in parallel. When our capacitors are in parallel, the total capacitance just adds up. So for this capacitor that I'm going to call capacitor, the combination of these two capacitors, I'll call that total capacitance C sub BC. And that will equal the capacitance of capacitor B plus the capacitance of capacitor C. So that will be 1 microfarad plus 3 microfarads. So I could replace these two capacitors in parallel with a capacitor with a capacitance of 4 microfarads. So that's this one right here. Okay, these two capacitors in parallel, that's capacitor, we'll represent that as C sub DE. The total capacitance of those two in parallel will be the capacitance of capacitor D plus the capacitance of capacitor E. So that will be 6 microfarads plus 2 microfarads, and that will give us 8 microfarads. So this combination of capacitors I can replace over here also with a capacitor that has a capacitance of 8 microfarads. Okay, so now we see that we have in this sort of equivalent diagram here, where we've reduced some of those capacitors down, we have in each of these branches capacitors that are in series. Let's go ahead and find the total capacitance of these capacitors in series with each other. So we're going to find the total capacitance of these two in series. We're going to replace it with one equivalent capacitor in our next diagram. We can combine these two capacitors in series and replace it over here in this diagram. Okay, so when we have capacitors that are in series, the capacitance is an inverse relationship. This time I'm going to call this one capacitor A, this one capacitor B, this one capacitor C, and this one, capacitor D. Okay? So the total capacitance of the combination of A and B, 1 over CAB, equals 1 over CA plus 1 over CB. So we have to take the inverse of that in order to get the total capacitance of these two together. CAB equals the inverse of 1 over CA plus 1 over CB. And I can write it like this. We can write the inverse as this whole thing to the power of minus 1. This is the same thing as saying 1 divided by all of this stuff added together. Right? And that gives us a total capacitance of, this will be 1 over 4 microfarads. What's that? Plus 1 over 4 microfarads. It's the minus 1. C sub B, capacitance for the capacitor that we're representing as B, is 4 microfarads. So this gives us a total capacitance of 2 microfarads for the combination of these two in series. That makes sense because when we have combinations of capacitors in series, their total capacitance is always less than the capacitance of any of the individuals. Now for our total capacitance of C and D, that will be 1 over the capacitance of the total capacitance of C and D equals 1 over the capacitance of C plus 1 over the capacitance of D. So this is the capacitance of these two together, CD, is equal to 1 over CC plus 1 over CD, all to the minus 1. Okay? So that's equal to 1 over, we've got this as 8 microfarads, plus 1 over 8 microfarads. That's this one here. And we take that all to the power of minus 1. That gives us a total capacitance for these two in series of 4 microfarads. Okay. Then in my equivalent circuit that I can draw over here, these two capacitances combined together gives us 2 microfarads. These two capacitors combined together give us a total capacitance of 4 microfarads. And now, to get the final total capacitance of that one capacitor that we could replace all of these capacitors with, we just have to combine these two in parallel with each other. And when our capacitors are in parallel, the total capacitance just adds together. So, well, this time we'll call this one A, and we'll call this one B. Okay? So CAB will equal CA plus CB. And that will equal 2 microfarads plus 4 microfarads. This one was 2 microfarads, this one was 4. And that gives us, finally, a total capacitance of 6 microfarads for this combination of initial capacitors. Okay, so we had to break up the combination of capacitors into different bite-sized pieces. It made sense to think about these two with these capacitors in parallel, combine them, make our new diagram here. We combine our capacitors that are in series with each other to make our new diagram here, and then we combine these that are in parallel with each other to get us our final total capacitance. This is the capacitance, 6 microfarads, is the total capacitance of this combination of capacitors. It's also the total capacitance of the capacitor that we could replace this whole combination with in a circuit. All of that was part A, finding the equivalent capacitance of this combination of capacitors. Now, we're going to take this combination of capacitors and connect a 12-volt battery across this combination of capacitors. So here's my 12-volt battery. I've got the positive terminal and negative terminal here. We're going to find the charge on our 4 microfarad capacitor right here in this very first diagram. So I'm going to call that Q sub 4 microfarad equals question mark. And we're also going to find the voltage drop across it, V sub 4 microfarad equals question mark. To find this, we have to remember that the charge for all capacitors in series is the same. Okay? So if I come over here and I think about, let's see, we've drawn a whole bunch of these diagrams right here, which are essentially the same. We've just combined some of these capacitors together. So in this diagram right here, we've got this equivalent capacitor, okay, which was a combination of these two in series. Right. So when we have capacitors in series, the charge on them is the same. So that means that the charge on each one of these capacitors here is the same as the charge on this capacitor. Since this capacitor is what we could replace both of these two in series with. So if we know the charge on this capacitor, we know the charge on both of these capacitors, and this capacitor right here is the same as this one here, okay? So we know that. And we also know that the potential is the same for all capacitors in parallel here. So these two capacitors are going to have the same potential across them. We also know that the potential for capacitors in parallel are the same. So both of these capacitors are going to have the same potential across them, which is our 12 volts from the battery. Right. So with that information, we can find the charge on our 4 microfarad capacitor by thinking about the charge on this capacitor right here. So this capacitor, the charge on it is equal to the capacitance times the potential. So the capacitance of this equivalent capacitor was 2 microfarad. And the potential is going to be our 12 volts. When we have both of these capacitors in parallel, the potential between the plates of those capacitors is the same as the potential that's being supplied by the battery. Because we could imagine that these are also connected to our 12-volt battery, okay? So that means that both A and B are experiencing a potential of 12 volts. If we take 2 microfarads times 12 volts, that gives us a total charge on this capacitor right here of 24 microcoulombs. So remember that the unit of charge is coulomb. This C here represented a capacitance. So the charge on this capacitor was 24 microcoulombs. These two in series created this equivalent capacitor here. So the charge on the plates of this capacitor is the same as the charge on the plates of both of these capacitors, okay? And this capacitor is the same as this one out here. Okay, so that means that if the charge on our plate on the top over there was 24 microfarads, or sorry, 24 microcoulombs, then the charge on this capacitor out here is also 24 microcoulombs. Okay? And then to find the potential across this capacitor, that one is a little bit easier. Okay, so we know that Q is equal to C times V. We need to solve this for the potential across this capacitor. Now we know Q and now we know C, or we already knew the capacitance to start with. So the potential across this capacitor is going to be the charge across it divided by its capacitance. And the charge was 24 microcoulombs, and the capacitance was 4 microfarads. So when you divide something with a micro by a micro, then those units essentially cancel each other out, and we're going to be left with something in units of volts. And so this potential across this capacitor out here is going to be 6 volts. Okay, so 24 microcoulomb divided by 4 microcoulomb, that's the same thing as 24 times 10 to the minus 6 coulomb divided by 4 times 10 to the, times 10 to the minus 6 farad. So you see that the times 10 to the minus 6 cancels here, and that just leaves us with, yes, 6 volts of potential across this capacitor out here. Okay, so that was a bit of a doozy. We had to break down our capacitor and create these 4 different diagrams to represent the equivalent capacitance of this combination of capacitors. Combine different chunks together to create our equivalent diagrams here, and we keep on simplifying and simplifying our diagrams by thinking about, are these capacitors in series or parallel, and how can I add them together so that we can finally combine them to create one total capacitance, or one equivalent capacitor that we could replace all of these capacitors with. And then we had to really think about our rules for capacitors in series and parallel in order to find the charge and the potential across this first capacitor out in front.